Thanks. So if we have a ionic species, right, a nonpolar solvent's not going to be able to dissolve that. Okay, so therefore the nonpolar aprotic is going to be problematic. But then the DMSO is a polar protic, actually very polar. So that would be the solvent that I would want, right? It can solvate the anion, the potassium propoxide, right? And it's aprotic, so it's going to favor SN2 reactions. Okay, questions? Sorry, that took a long time. Technical difficulties. All right. Okay, let's do a quick one. This one hopefully will take you less than 2 seconds. Okay, this is the only specific pKa question you'll get. And the answer is 15.7, right? That's the one I want you to know. The rest of them, it's helpful to know them. I won't ask you them directly. It is important to know ranking, right? This is more acidic than that. And it's important to know how to use pKa's, but I'm not going to say what is the pKa of a ketone. Yes, sir. It's your reference point, right? So we think about it, water kind of gives us our base reference point. It's kind of like, what number would I want you to know if we were talking about pH scales? 7, right? So it gives me the reference point. If somebody says, you know, it has a pH of 2014, I'd be like, what? Right? And so it kind of gives you what is the general. So the pH of a neutral solution is 7. You should know 7. pKa's, water is a good one to know, right? And it's an easy one to remember. You know, I could have picked acetic acid, you know, 4.8, right? But water is just more general, and it gives you the reference points, right? I could have also picked alkanes, but water is a solid one to remember, so you know what the scale is. Okay. The other reason that one is helpful is whenever you get to biochemistry and some of the biochemistry calculations, you'll always be referring back to water, right? Everything's in a water-based system. So, okay. So that one, know that one. Let's see. Okay, so if we look at this one, right, just identifying the parts of the reaction, we can look at these. If we know that a sulfuric acid is an acid, we can just go ahead and put that down. But what we can really do is look and see what happens to these on the other side, right? What happened to the ether, the oxygen here? The oxygen abstracted a proton. If this abstracted a proton, then that would be my base. I can do the same thing here, right? What happened to the H2SO4? It lost a hydrogen. If it lost a hydrogen, that means it's giving up a hydrogen. That means it's going to behave as an acid. right? The other part of this that's important is to understand that the acid becomes the conjugate base, and that base becomes the conjugate acid. Now, would this reaction be going forward or backwards? It's going to go forward, right? The hydronium, the acidity of the hydronium here is less than the acidity of the H2SO4. This is about 1 to 0. This one is -7. Okay, so what would be the conjugate acid of this base? Okay. So if this reacted with a generic acid, that's going to be my conjugate base. I've been all kind of technical. So more or less, I'm just adding a proton, right? That would be the conjugate acid. If there's a conjugate base, I'd be removing a proton. Okay, here, let's look at this reaction. Okay, so does the reaction proceed in the forward direction or the reverse direction? For this one, we want to look at the stability. Of our conjugate bases. So the alcohol, the phenol here, and the thiol both appear stable. So it's easier to think about stability when we look at the sulfur minus versus the oxygen minus. Now, one of the things that came up in the office hours on Tuesday was what about atom between oxygen and sulfur? The difference between a carbon, a nitrogen, and an oxygen atom acidity is very distinct, right? We've got 50 to 35 to 15.7, right? So it drops really quick. When we look at oxygen to sulfur, they're in the same row, right? So they have the same number of valence electrons. The difference there is going to be the stability based on the size of the atom. And so if we look at oxygen, 15.7, to thiols around 9, right? So we're not dealing with as big a difference. It's still several thousand, but it's not, you know, millions of factors. Okay, so when we're looking at those, there's a little bit of difference. The other thing we have to remember is that although orbital is one of the last things on the list of atom, resonance, inductive, and then orbital, it is important to make sure we're comparing apples to apples when we're looking at orbitals, right? So are we dealing with a nitrogen sp3 to a carbon sp3, or we're dealing with a nitrogen sp3 to a carbon sp, right? That makes a big difference for those two because of the way they stabilize. Here we've got a sulfur sp3 versus an oxygen sp3. Both of them have resonance, right? Both have resonance into the ring. So therefore, the only difference in these two is going to be the atom, right? And so which one is more stable? The sulfur is larger. It can stabilize that negative charge more, right? We have more place to delocalize, not delocalize, but polarize those electron density. And so therefore the sulfur is going to be more stable. Okay. So if that's more stable, that means that the reaction is going to actually go in the reverse, the back reaction. Questions about that one? The one that's going to catch you quite a bit is going to be that nitrogen sp3 negative, right? And the carbon sp negative, right? The carbon negative in that case is more stable than the nitrogen. The sp carbon negative is more stable than the sp3 nitrogen negative. That one's the one that flips, and that'll be the most common one that usually catch you off. This one in the practice problems caught some people off because of the sulfur on the quiz. There was a difference between a sulfur non-resonance and oxygen resonance. That one caught a few people, mainly because of the resonance, right? And the fact that they're not going from carbon to nitrogen negative, but they're going down a row. I mean, down a column. Okay, let's look at acid strengths. Okay, which of one of these is the strongest acid? Okay, so if we look at this one, one of the things we can do is look at all the conjugate bases. That'll help us think about what's going on. Okay, so if we look at those there, all of them have oxygen negatives. All of them have resonance. So what that leaves is just the inductive. And if we think about the inductive is based on electronegativity. And the electronegativity for this is going to be fluorine is greater than chlorine, which is greater than iodine. So if we had to rank these, we'd have 1, 2, 3, 4. So the most acidic is going to be the fluoride. The other thing to realize here is they're all attached to the beta position. So inductive effect also has a distance. So always check that as well. So here everything is the same except the halide. So we're really looking at electronegativity of the halide is what distinguishes these. let's take a little time on this one. Can this base exist in liquid ammonia, NH3? All right, this seems like a really tough question. Can something exist in a solvent? For this one, the thing to think about on this is we're really looking at a reaction, right? Something can exist in a solvent if it doesn't react with the solvent, or if the reaction with the solvent is not a significant reaction with the solvent, meaning it could react with the solvent, but it would actually rather not react with the solvent. So therefore, if we think about this one, the way we would set this up is, could this react with this? Now, if it had been an aprotic solvent, no protons, the fact that I have a carbon negative there may not have had any difference. If I didn't have an electrophilic solvent, there also I may not have saw. So the things I'd be watching for is solvents that have protons and solvents that have electrophilic positions, because this is a potential base or nucleophile, right? So then the question becomes, this is a base nucleophile, right? So then the question is this a potential acid or electrophile? Well, it's got an available proton, so therefore it is potentially an acid. So that reaction would be base pulling proton oops, correct that, that should have been a 2. Then the question becomes, is this more stable than that? If the starting compound is more stable, then yes, it could exist in that solvent. If the product, this NH2 minus, is more stable, then it would not exist, right? It would react as soon as I threw it in there. So if we think about this, this is an sp3 carbon, this is an sp3 nitrogen. Which one of these two is more stable? The sp3 nitrogen is more stable than the sp3 carbon. Right? So that means that this reaction going forward is the reaction that's going to occur. Yes. You could guess it on pKa's, right? So the pKa here would be 50, right? And the pKa here would be around 35. And you could have also known just the relative pKa's, right? You could have compared the conjugate acid that to the relative pKa of that, right? Knowing that the sp3 nitrogen is more acidic than the sp3 carbon. All right, so that's going to go forward. So the answer here is no. You know, that base cannot exist in liquid ammonia. So the way to look at these reactions is to look and see if there's going to be a reaction between the reagent and the solvent, and if that reaction is going to be favored. In this case, it is favored. It will proceed forward. So anytime I throw this carbon anion into ammonia, it's going to react, and I'm going to be left with just the nitrogen, the amide negative. Okay, let's see, we got a couple more. Let's take a little time and look at this one. So it is helpful here to think about what potentially could be going on, but we also have to think about our reactants here. And so we've got a positive and a negative. This is a good nucleophile. Right, we've got an aprotic solvent, aprotic polar solvent. Right, and again, drawing the structure always kind of helps. Right, we have no protons attached to oxygen negatives, so it's aprotic polar. And then we get, so that is suggesting SN2 type process. This is suggesting an SN2 type process. And then here we see that we have a stereospecific product that also would suggest an SN2 style product. And if it's SN2, that means we have inversion. So the product we need to start with needs to be something like this. Since we're having inversion, everything looks like it's an SN2, I need to have the leaving group in an opposite direction, opposite side of where my nucleophile came in. Then the question becomes the leaving group. There are some leaving groups that actually won't work well. So chloride wouldn't work well, bromide wouldn't work well. Why? The iodine's more stable, right? So it would go backwards. So these would go backwards. So here I need a nice polarizable, very stable leaving group. Okay, one of the ones that we have, right, is this tosylate. Okay, now if it had not been iodine, there might have been several good leaving groups, but the iodine specifically, I need to be careful about my leaving group. Now this will most often be multiple choice type question. This is, I mean, picking the right leaving group out of the assortment of millions of possible leaving groups is a little tough. So this would be more of a multiple choice question. But the thing to realize here is that what you think of as good leaving groups, and they are, like chloride and bromide, happen to not be great leaving groups for iodide replacement, right? Because the iodide substitution would actually go backwards. So you need something that's even a better leaving group than iodide. And there's not many of those that we've seen. Right? And one of them is the tosylates and the mesolates. Yes. I'm going to post some of the action center problems. I didn't do